All right. Hello. Now I will talk about hyperbolicity and topological conjugacy. So we're gonna see some definitions that are introduced us to the Grobman-Hartman theorem. So first, are gonna find what is an hyperbolic critical point. So we'll recall that a square matrix is said to be hyperbolic if all the eigenvalues have non-zero real part. And we will let f be R1, a C1 function from Rn to Rn. So point x naught of Rn is said to be a hyperbolical critical point of the equation x prime equals fx if f at x naught is 0 and the matrix, the Jacobian matrix, the differential matrix of x naught of f is hyperbolic. So the eigenvalues have non-zero real part. So given an hyperbolic or critical point, we will consider the linear equation x prime equals a of x, where a is just the Jacobian at x naught. So the solutions, we have studied that they are given by the exponential of a at t minus t0. So we will call, given an hyperbolic or critical point, we will call the stable and unstable spaces of x0 this way. The stable space are all the x in Rn such that the exponential of at of x goes to 0 when t goes to infinity, and the unstable space is are all x that tends to 0 when t goes to negative infinity. So we have this proposition here that says that if we have an x naught, an hyperbolic critical point of the equation x prime equals f of x, then these two spaces, this stable and unstable space, are linear subspaces of Rn, and moreover, we have that Rn is equal to the direct sum of e to the s and e to the u of, the stable and unstable space. And for every x and y on the stable and unstable space, and every real number t, we have that the exponential of at of x is also on the stable space, and the exponential of at of y is also on the unstable space. So here's the proof. Given that the Jacobian matrix of x naught has no eigenvalues with 0 real part, we can write a Jordan form of the matrix this way. We have the block of all AS, being AS the block with the block of eigenvalues with negative real part, and A sub u be the eigenvalues with real positive part, positive real part. Why? Because let's recall, for example, when you have the limit as e of negative t, as t goes to infinity, that goes to 0, and e to the t goes to 0 when t goes to negative infinity. So that's like the intuition of why the stable space is with negative eigenvalues and the unstable space is with real positive real part of the eigenvalues. So by proposition 2.27 that I have here, if we got a matrix with only eigenvalues with real parts, we have that the norm of the exponential at is bound by c e to the negative dt for some constant c and d, and t bigger than or equal to 0. And the norm of the matrix exponential is just any norm in Rm, because they are all equivalent, right? So yes, sorry. So given this property, we have that the limit is bounded as t goes to infinity is bound by this, and this goes to zero. So it also goes to zero when t goes to infinity, given x in the stable space. Well, not the stable space, but in Fs, which is the decomposition with respect to As and A sub u. And also this goes to zero when t goes to negative infinity for t in FAU. The associated decomposition with respect to the negative real, sorry, the positive real part. So what we see here is they are equivalent, that Fs and Es and Fu equals EU. So this gives us the first property, right? Because Rn is the direct sum of these two spaces, and these two spaces are equivalent to this the decomposition at the stable and unstable space. So for the second property, note that these two matrices commute a tau and a t. So the exponential of this is equal to the exponential of that for every t and tau in R. So in particular, if we got x in the stable space and t in the any real number, we will have that the matrix exponential of 8 tau times the matrix exponential of 8 t of x is just equal to the exponential of 8t times the exponential of 8 tau times x. Now, since x is a stable on the stable space, the limit goes to 0 when tau goes to infinity. So we will have that the limit it goes to 0. In other words, a to the exponential of at of x is also on the stable space. And analogously, we will show that if we have a y in the unstable space and any real number t, we will have that the matrix exponential of at of y is also on the unstable space. All right, so here we, by the proposition, we see that given a hyperbolic critical point, it gives two spaces that are on direct sum. So we will define these projections, P sub S and P sub U. P sub S with regards to the projection on the stable space, and P sub U on the unstable space. So I will just call them the stable projection and the unstable projection, because given X in Rn, there is a unique Y in the stable space and Z on the unstable space, so that X equals Y plus Z. And we can verify easily that these two transformations are projections indeed. So there are linear transformations first. The projection of Rn gives us the stable space, and the projection of Rn gives the unstable space, and the composition of the projection with itself gives us back the projection. And we can also show that this holds that the stable space equals to the real part of the G stable and the imaginary part of G of S, and respectively with the unstable space, where GS and GU are the subspaces of C to the n, the complex numbers generated by the root spaces of eigenvalues with negative part and real part, positive real part. And we can see that GS are just all X and Cn, such that the Jacobian at x naught minus lambda, the identity, raised to the k equals to 0 for some k in the natural numbers. And with the real part less than 0 and the real part bigger than 0 for the unstable part. So now we see, now we have the Grobman Hartman theorem. So what does this theory say? it connects the solutions with the hyperbolical critical points. Yeah, we could say that. So the solution of x prime equals f of x, and the solution of y prime equals the Jacobian of x naught of f of y are topological conjugates. That is, they are similar. We have here the definition. Just as a reminder of linear algebra, we have that two matrices are similar if there is some inverse matrix such that A equals, let's call it P inverse B P. So we have that the solutions are similar topologically in the neighborhoods of x naught and 0, because you know for the matrix you have the what on 0, the initial value will be 0. So given the linear algebra refresh, so what the topological conjugate means is that if we have the solution phi of t and psi of t and phi of t are solutions of the previous problems, initial value problems. So we will have that there is a unique homeomorphism H from U to B, where U and B are neighborhoods of x naught and 0, such that H of x naught equals 0 and H of phi t equals to H of psi of t equals phi of t of H. In other words, the psi of t equals to, since the H is homeomorphism, the inverse exists and the inverse is continuous, and equals H inverse of phi of t composition with H. Whenever Z and phi of t are both in the neighborhood of x naught. So this guarantees that the phase portraits of the equations 4.3 are homeomorphic respectively in neighborhoods of x naught and 0. You can see it in the figure over here. So when we apply H to the neighborhood of x naught, it goes this way. We have here the stable space goes to 0, and the unstable space over here, and the same over here. Sorry. So before we go to the main dish, we have this theorem that we have to prove. So what happens when we disturb the hyperbolic matrix? Okay, so that's gonna help us prove the next theorem. So we'll give a result on the existence of topological conjugacies for the perturbations of a linear equation x prime equals ax, where A is a hyperbolic matrix. So given an n by n hyperbolic matrix and let G be a bounded function such that G of 0 equals 0, G goes from Rn to Rn, and G of x minus G of y, the norm of that is less than or equal to delta times the norm of x minus y. So it's Lipschitz, I guess. So for any sufficient small delta, there exists a unique bounded continuous function eta from Rn to Rn such that eta of 0 equals 0, and we have H equals to the identity plus eta satisfies this H of the exponential of at equals phi of t of H, where phi of t is the flow by the equation x prime equals ax plus g of x. So it's the perturbation of the initial problem, right? X prime equals a of x. And the most important thing, H is an homeomorphism. So yeah, the matrix exponential of AT is topological conjugate of phi of t. So the proof is very long. So it's divided in, if I recall correctly, 7 steps or 6 steps with 2 lemmas. So let's start. The existence of global solutions. So first we need to show that x prime equals ax plus g of x has a global solution, or the final flow, as we said here. So each solution satisfies this, the general equation x, the exponential of at minus t0, x at t0, t naught, plus the integral from t naught to t of the matrix exponential of a minus a of t minus s, a times t minus s, applied to g of x of s. For t corresponding to the maximal interval I of x. So yeah, the function that goes applies t and x to a of x plus d of x is continuous, locally Lipschitz in x, and thus we can apply the Groundwater theorem. So it follows from this whose theorem did I say? Picard theorem, I meant to say, sorry. So yeah, by the inequality on 4.5, we'll have that the norm of x of t is less than this, and this is going to be less than delta for t bigger than t0, greater or equal than t0 in I of x. And by Groundwater's lemma, now we have Groundwater's lemma, we obtain the following inequality, which is equivalently to saying that x of t is less than or equal to the exponential of the norm of a plus delta times t minus t0 times the norm of x at t naught. So this implies that each solution x of t is defined on the interval t0 to infinity. Otherwise, the right endpoint b of the interval ix will be finite, and by 4.9, by the previous inequality, we'll have this, that the limit as t approaches b from the left of x is going to be less than this, which contradicts the theorem 1.46 on the behavioral solutions at the endpoints on the maximal interval. And similarly, we will see that the solution is also defined for minus infinity to t0. So the solution is global, which is good. Step 2, construction of an auxiliary function. So we have x0, x naught, big x naught be the set of bounds continuous functions eta from Rn to Rn with the eta not eta 0 equals 0. So this space is a complete matrix space with this distance. It's not hard to see. So we will define this transformation G in this complete matrix space. Okay, given that G of eta of x equals to the integral from 0 to infinity of the projection on the stable space, the stable projection of this guy, minus the integral from 0 to infinity of the projection on the unstable space of this other guy when we have negative now a tau here. And it's going to be equal to this integral when we swap change when we make a change of variables, change the limits of integration. Sorry, for each eta in x naught and x in R, where, as I said, PS and PU are the projections over the stable and stable space. So G is well defined. Since A is hyperbolic by proposition, by the previous proposition that we saw, there are some constants such that this happens. I mean, they're bounded, and there are less. So the projection on the stable space of the exponential of a tau of eta of the exponential of negative a tau is going to be less than or equal to c times the exponential of negative mu tau times the norm of eta, or the infinity norm, where the infinity norm, as we know, is just a supremum of these norms. Since it's a bounded function, bounded continuous function, we have that the supremum exists. So it follows from these two inequalities that this integral is less, after all, is less than 2 times c over mu times the norm of eta. So the transformation is well defined, and by the norm is less than this for each x in Rn, and the function is bound but for each eta. So we will show now that it's continuous. So given x and epsilon bigger than 0, it follows from this inequality that there is some t bigger than 0, such that the integral from t to infinity of this norm plus the integral from t to infinity of this other norm is less than epsilon. So for each x and y in Rn, we have the following: the g of eta x minus g of eta y is less than 2 times epsilon plus these integrals. And so for each delta, this function is uniformly continuous on the set, on this compact set, because continuous functions are uniformly continuous on this compact set, as I said. Yeah, 0t is a compact set, and the closed ball of x radius delta is also a compact set. So there is some delta bigger than 0 such that this inequality holds for each tau in the interval from 0 to t and each y on the ball. So there exists some delta, which we can assume that is the one before, such that this happens for every tau and y on the ball of radius delta. So from the inequality 4.16, this inequality, we'll have that the norm of the difference of g of eta of x minus g of eta of y is less than 2 epsilon plus 2 times c times t epsilon. So we can redefine epsilon to be whatever we want, and this is just a constant. So epsilon, for any epsilon, this inequality holds, and g is continuous. G of eta is continuous. Moreover, we have that g eta of 0 is 0, so the image of g is contained on x of 0. So let's recall what we showed that on this step. So we found a transformation g on a complete matrix space such that it maps these types of functions that are continuous, bounded, and go at the at t equals 0, there equals 0. So the next step. So given any eta, we'll call g of eta equals to g of x, where g of h of x, where h is just the identity plus eta. So the function g of eta is bounded because g is bounded, as we said before. So it follows from the previous inequality that g of eta of x minus g of eta of y is less than equal to delta times the norm of x minus y plus delta times the distance of eta of x minus eta of y. All right. And moreover, g of eta of 0 is equal to 0. So g of eta is in x naught. So this identity 4.6, let's see again, what's 4.6? This equality is the same as saying that g of capital G of g sub eta equals to eta. So the proof of this lemma, from the Leibniz rule, we have that this partial derivative with respect to t is equal to all this calculation over here at s equals 0. So after doing all these steps, we show that the function, the function y of t equals h of e, the matrix exponential of at of x, satisfies the equation 4.7, since y of 0 equals h of x. We have that h of the exponential of at of x equals to phi of t h of t. So as now we assume that 4.6 holds, since h equals to the identity plus eta, we can rewrite this identity in this form, that identity plus eta equals to phi of t of h of the exponential of negative at. On the other hand, by variation of parameters, we have that phi of t of x equals to this this function a of at of x plus the integral from 0 to t of this matrix exponential times g of phi of t of x, phi tau of t x. I meant. So using 4.6 and 4.19, this equality and the previous equality, we have that eta of x equals phi of t of h of the matrix exponential of negative atx of x, at times x minus x. So this is equal to all this integral, all this. So we end up with the matrix exponential of a of t of eta of e to the negative at of x plus the integral from 0 to t of the exponential of a tau g of h of the exponential of negative a tau of x. So it follows from the previous result that this projection goes to 0 when t goes to plus infinity. So by the equality in 420, we have that projection of eta of x is equal to the integral from 0 to infinity of the projection of s of e to the a tau times g of h of the exponential of negative a tau x with respect to tau. So on the other hand, from the theory equality, from here, it follows that this equation, it follows this equation. The exponential of negative a tau at of eta of x equals to eta of e of negative at x plus the integral from 0 to infinity of all these things. So by substituting x by e to the at x, we obtain the following, that e to the negative at times eta of e of at x is equal to eta of x plus the integral from 0 to t of e to the negative at g of h of the matrix of e a tau x. So it follows, and obviously this was for the stable space and the unstable space. So we obtain that eta of x equals to the projection of the projection over S and the projection over U of the stable and unstable space, but this is just G of eta of X. That is the result we wanted to show. So we got all this, this work to yield the result that eta of X equals to G of capital G of G sub eta, which G sub eta is just the identity, H is the identity plus eta. So this is nice. So now let's construct the conjugacy. So we show that the equation G, capital G of G sub eta equals eta has a unique solution eta. So another one, for any sufficient small delta, there's a function eta such that the equality holds, the equality we desire. The equation has a solution. So we define a transformation f given by this. F of eta equals to G of G sub eta. So F is a construction. That's what we're going to show. That's why we had that G is a transformation from x0 to x0, so that we have a contraction, and by the Banach's contraction principle, we have a unique solution. Okay, so that's what we had here. We are showing that F is a contraction, so the norm of eta of x minus the distance between f of eta of x and f of psi of x is less than a constant times the distance between eta and x and psi. So and this constant is the construction, the constant is gives that f is a construction for any small delta. So since x0, x0 is a complete matrix space, and the image is contained on x0, we have a unique eta, a fixed point where where f of eta equals eta. So by this lemma, by the previous lemma, the function eta satisfies that h of the identity, h being the identity plus eta, is a homeomorphism. I mean, it remains to show that h is an homeomorphism. So we have to show that, well, we know it's continuous because it's on a matrix space of continuous functions, bound continuous functions. So we have to show that there is an inverse and the inverse is continuous. So step 5, existence of inverse. We show that h is surjective. Sorry. So given y in Rn, the equation h of x equals y has a solution of the form x equals y plus z, if and only if z is equal to negative eta y plus z. So by Brouwer's fixed point theorem, any continuous function on a closed ball in Rn has at least one fixed point, and we can. It's another way of saying the Banach principle, contraction principle. So applying this function to the theorem, given the function z goes to negative eta of y plus z, the closed ball, we conclude that there is at least one point z in B satisfying the equation, which shows that H is surjective. So H is subjective. Let's see, J is injective. H is injective. So given X and Y, if we have that the image equals the same, it follows that H is the identity plus eta of t. Eta equals H equals identity plus eta. So we have that if they're both equal, applying this to them is also equal for T in R. And then we have that the exponential of AT applied to X minus Y is equal to negative eta E, the exponential of ATX plus eta exponential of ATY. So if we have that the stable projection of X minus Y is not zero and this unstable projection is not zero, then the left-hand side will be unbound while the right-hand side is bound. So this is a contradiction. So that arises that the stable projection and the unstable projection equals zero. So we are talking about that X minus Y equals zero. So X equals Y. So yeah, we have it's surjective, injective, so it's bijective. So there is an inverse. So we have to show that the inverse is continuous. So if let's recall the invariance of the main theorem. If f from U to Rn is an injective function in an open set, then the image is an open set, and when we restrict it to the domain U, it is an homeomorphism when we restrict it to the image. And it's a complicated theorem, at least for me. So H is continuous and bijective. So for the theorem, it is an homeomorphism, and that's it. The easiest step, if I dare to say. So with all of this, we have shown a relationship between hyperbolic points and solutions of some system of equations, of perturbations of the original hyperbolic, let's say the hyperbolic problem. So we have now the consequence, the Grobman-Hartman theorem. Grobman-Hartman theorem. So given f from Rn to Rn be a function of C1 and let x not be an hyperbolic critical point of the equation, x prime equals f of x, then if phi of t, the psi of t and phi of t are the solutions of the initial boundary problems in 4.3, where psi of t is the solution of the x prime equals f of x, and psi of t is the solution of the of y prime equals the hyperbolic, the Jacobian at x naught of f of y, then there exists an homeomorphism that relates u and b, where u are neighborhoods of x0 and b is the neighborhood of 0, such that h of x naught equals 0, and we have the phi of t, psi of t is topological conjugacy of phi of t. Whenever z and psi of z is in U, when both are in U. So with a loss of generality, we will assume that x naught equals 0. We're going to show that making a change of variables. So we note that the matrix A is hyperbolic, and the function G here defined by defining the difference between f of x and the Jacobian of x naught. X naught we assume to be 0 now. Jacobian at 0 of f, G being this difference, okay? G is of C1 and G of 0 equals 0. So we want to show, we want to apply the previous theorem we just proved. Okay? We did some hard work on it, we want to use it. So we have to show only that the property 4.5 holds. Let's see, what was that again? We want to show that the difference, the distance between g of x and g of y is less than delta times x minus the distance between x and y. Okay, so let's see. How do we prove that? So in general, this property may fail. So that leads us to modify g outside of the neighborhood of f of 0. So given delta bigger than 0, we'll take r so small that the supremum of this, the Jacobian of g at x, where x is in this ball, is less than delta over 3. So we can do this because this function is continuous and at 0 equals 0, and g of 0 equals 0. It follows then the mean from the mean value theorem that this supremum of g of x is of the norm of g of x is less than delta times r over 3. So we'll now consider the function alpha from Rn to 0, from 0 to 1, the closed interval of we'll have this function of class C1 where alpha of x equals 1 for x in this ball and 0 outside of the ball of radius r, and that the supremum of the norms of the Jacobian is less than 2 over r. So for the function defined on g dash g, well, let's call it, we'll call dash g equals to alpha x times g of x. So dash g of 0 equals 0, and by the previous inequalities, we have the following, that the norm of the Jacobian of g dash at x is less than delta, applying the inequalities. It follows from the mean value theory that property 4.5 holds for the function dash g. So we can apply theorem 4.4 to find a homomorphism h equals identity plus eta, satisfying that the exponential of at is a topological conjugacy of psi of t dash t, where this is the solution of the initial value problem x prime equals ax plus dash g of x and g of 0 equals to 7. But since g coincides, g dash g coincides with g on the ball, we have that they are equal whenever the norm of z is less than r over 3 and the norm of psi of t z is less than r over 3. So that establishes the identity 4.4 for any t and r and z such that this holds. So this, let's say, neighborhoods. So that's all I have time for today. The next are some interesting properties that I do recommend to read on your free time. So that's it. Thanks for watching and see you in another one.